In the previous session, we saw the expansion of e to the power of x in terms of powers of x. So we saw as we take more number of terms, the series tends to converge towards the function. Now let's see how we arrive at this series. How do we know that this works like this? So to do that, let's start our next session. Let f of x be a function which can be expanded in powers of h, and the expansion be differentiable any number of times. What that means is we have a function f of x plus h is equal to h to the power of 0 times f naught x by 0 factorial plus h1 times f1 x by 1 factorial plus h square times f2x by 2 factorial plus h cube times f3h by 3 factorial and so on. So our general term will become h to the power of n times fn x by n factorial. Now here, one thing that we have to be clear about is that as far as the exponents of h are concerned, they represent the powers. Whereas when I say f1, f2, f3, f4, they are the first, second, third, and so on derivatives of f. And f0x is basically the 0th derivative, which means basically the function itself. Let f of x plus h is equal to, so this is what Taylor's theorem. Now here we are taking a naught plus a1 dot h plus a2 dot h square plus a3 dot h cube plus a4 dot h to the power of 4. Now where a0, a1, a2 are functions of x alone, what will be the first derivative of this? Here if you notice, a0 is a constant. So when we take the derivative, it will become 0. So it will disappear. Now a1 times h, its derivative is a1. Here we have a2 times h square. So 2 comes down and the power reduces by 1. So we end up with 2a2 times h plus 3a3 times h square plus 4 comes down, 4a4 times h cube. So this is our first derivative. Now let's look at the second derivative. So second derivative is nothing but the derivative of the first derivative. So we end up with here, if you notice, a1 is a constant, so it disappears. 2a2 times h, power is 1, 1 comes down, and this becomes h to the power of 1 minus 1, which is 0. So which means 1. So 2a2 plus 3 times 2 times a3 times h. Similarly, 4 times 3 times a4 times h square, and so on. Similarly, the third derivative, that becomes 3 times 2 times a3. The first term disappears because it's a constant. Plus 4 times 3 times 2 a4 times h, and so on. And let's take the fourth derivative. This becomes, the first term disappears because it's a constant, plus 4 times 3 times 2 a4 times h disappears, and so on. We keep doing this. Now that we have these derivatives, let's say h is equal to 0, which means what? Remember I said f0 of x is nothing but f of x itself. f0 of x is the first zeroth derivative of f of x, which is nothing but the function itself. So f of x, here all the terms have h except a naught. And since we have said h equal to 0, all the terms disappear except a naught. So f of x equal to a naught, which implies a naught is equal to f of x, first derivative. Again, we make h equal to 0. So all the terms become 0 except the first term, which is a1. So f1 of x equal to a1, which implies a1 is equal to the first derivative of f of x. Next, keep repeating that process. We take the second derivative, make h equal to 0. So all the terms become 0 except 2a2. So second derivative of f is equal to 2 times a2, which implies a2 is equal to second derivative of x divided by 2. The third derivative, all the terms become 0 because of h except the first term. So which means the third derivative of f of x equal to 3 times 2 times a3, which implies a3 is equal to f3 of x divided by 3 times 2. And let's take one more. Fourth derivative of f of x is equal to 4 times 3 times 2 times a4, which implies a4 is equal to f4 of x divided by 4 times 3 times 2. f1 of x, if it is just like that, we can write it as f1 of x divided by 1. And here the denominator we can write it as 2 times 1. Here we can write it as 3 times 2 times 1. Here we can write it as 4 times 3 times 2 times 1. So that it reminds you of a pattern of a factorial. What about this? A naught is equal to f of x. That also can be written as f of x by 1. But in this case, we can write it as 0 factorial, because 0 factorial is also defined as 1. So our general derivative becomes fnx is equal to n factorial times an, which implies an is equal to fnx by n factorial. Let's substitute these in f of x plus h equal to this expression. What do we get? We get f of x plus h is equal to f of x plus f1x by 1 factorial times h plus f2x by 2 factorial times h square plus f3x by 3 factorial times h cube, and so on. Now that we have this, let's make x equal to a specific value for x. So f of a plus h is equal to f of a plus f1a by 1 factorial times h, and so on. Now, if we take a is equal to 0 and h is equal to x, what happens? A is 0, h is x. So f of 0 plus x is equal to f of 0 plus f1 of 0 by 1 factorial times x plus f20 by 2 factorial times x square, and so on. So here what we are getting is a series which gives us the function f of x around a equal to 0. And this is called the Maclaurin series. So whenever we talk of a series centered around 0, we say, or centered at 0, we say it is a Maclaurin series. Now, instead of every time writing this cumbersome expression, we can use the summation notation. So in summation notation, this becomes f of x is equal to sum of, as n goes from 0 to infinity, fn0 by n factorial times x to the power of n. So this becomes the Maclaurin series short form or the summation notation. Now, if we are given this short form, we should be able to expand it by taking n equal to 0, then n equal to 1, then n equal to 2 to build up this series. Okay, now if we take h is equal to x minus a, then what happens? We have f of a plus x minus a. Here x minus a is the h, is equal to f of a plus x minus a times f1 of a by 1 factorial plus x minus a square times f2a by 2 factorial, and so on. And simplifying this, we get f of x, a disappears, is equal to f of a plus this series. And this is called Taylor series. Here, the focus is on the Taylor series centered at a. Again, in summation notation, it can be written as f of x is equal to the sum as n goes from 0 to infinity of fna divided by n factorial times x minus a to the power of n. So we have arrived at the expression that we have to use to figure out this series. Now, in the next session, we will look at how we can use this to arrive at the Taylor series for e to the power of x. Or if we are interested in centering at 0, we will be looking at the Maclaurin series. So that's it for now. But before I leave, let me remind you, there is a link to a PDF book which describes all of this in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.